Okay, this is a general two-stage least squares example, but for simplification, I allow only one endogenous variable, and there is no other coefficient. So the intercept is dropped, and there is no exogenous variable. But there may be multiple instrumental variables of m dimension. So, and it satisfies exogeneity and it satisfies rank condition. Okay, now let's think about the first stage equation. First stage is pretty simple, right? Our gamma estimator is just OLS. I'm going to write this as, say, mi of gamma, right? So minimizing a criterion function where mi gamma is defined as xi minus zi transpose gamma squared. And for simplicity of algebra, I'm going to write 1 over 2 here. Okay, this is, the typical OLS regression of x on z. So there is nothing much to say. And in this case, by the way, so what we want here is we want this converges to 0 in probability. Okay, so this is influence function and expectation of phi I equals to 0. Then we can apply the central limit theorem. So we want an influence function like this, and we know this influence function takes the form of say h inverse minus of h inverse times this, right? If you remember what we did in the earlier chapter, this is the influence function where, let me do the differentiation. The first order derivative is simple, zi times xi minus zi transpose gamma. And second order derivative is gamma. Second order derivative is zi transpose. Okay, so then it is minus zi transpose expectation inverse times, when you plug in gamma 0 here, this will become xi. So here you will have minus zi xi. So the minus signs cancel out, and the influence function from the first stage is this, which is the same as OLS as usual. Okay. And now let's think about the second stage regression. We are going to estimate beta hat as an OLS, right? So I'm going to write this as Li beta and gamma, where gamma hat is plugged in. And I will define gamma as y minus beta of zi transpose gamma, right? So in the place of x, I am using z prime gamma instead, because it is the fitted value. So we are using this criterion function. Okay, now from now on, let's do the math. It's pretty straightforward. Remember, I will just take the last equation first. We learned after the first order condition and linearization and rearranging the terms, then we know that this will be minus h inverse of the sample average of the first order derivative at beta 0 and gamma 0 plus g times first stage estimation error, where h is defined as expectation of the second derivative of criterion function, and g is defined as the expectation of the cross derivative gamma transpose. Okay, so this will be our last form, and of course we will derive the influence function from here. Okay, then let's do the simple math. differentiate with respect to beta, and then you get zi transpose gamma times yi minus, by the way, you have to put minus here, minus beta of zi transpose gamma. This is the first order derivative, right? And if you differentiate again with respect to beta, then you will get this simple zi transpose gamma squared. Because x is scalar, it is simple. And if you differentiate again, like with respect to gamma transpose, then you have to differentiate with respect to this and this, okay, one by one. So if you use the first argument, you will get this much, and if you differentiate the second guy, then you will get plus beta z transpose gamma times z transpose. Okay, this is the second derivative. All right, then now let's calculate the first derivative first. Beta 0 and gamma 0. If you plug in beta 0 and gamma 0, then this part will become ui plus beta 0 psi I as usual, right? So we know, I forgot, it is minus zi transpose gamma 0 times ui plus beta 0 psi I. Okay, that is the first derivative. Now let's think about h. H is easy, right? H is defined as zi transpose gamma 0 squared and its expectation, okay? And now let's think about g, like I'll take expectation over here, and this much will be ui plus beta 0 psi I. If you take expectation after multiplying with z, this term will go away after expectation. So we only care about the second part. So g is expectation of beta 0 times zi transpose gamma 0 times zi transpose. That is, so let me also write down. Phi was, let me see, where was it? Phi was here. So we have everything we need. Okay, so we will just combine them to have something. So let's first think about g times phi, right? G times phi here is, so I will rewrite the order of g in this way. Beta 0 is not random, so you can come out of the expectation, and you may write this as expectation of gamma transpose z. Doesn't matter, right? You may switch the order like this, and then you may write this as expectation of gamma 0 is not random, so you may rewrite this as transpose, excuse me, zi transpose. So this much is g, and you are going to multiply that here, zi psi. Here, excuse me, inverse. I forgot inverse. So you are multiplying inverse. So it will be simplified a lot, right? In the end, you are going to get beta 0 times gamma 0 transpose zi psi, right? That is g times phi. So we are working on, where was that? We are working on this equation, and we just calculated this much, okay? Now let's calculate a bigger part. So next, we are going to calculate summation of the first derivative plus g times, here, this guy. It is summation of the first derivative was this guy, okay? minus z transpose gamma 0 times ui plus beta 0 psi I. Okay, this is the first term. And the second term, here we know this is sample mean of phi I, and we just calculated g times phi I here. Okay, beta 0 gamma 0 transpose z I psi I, right? And you know it is anyhow it is scalar, so it equals to beta 0. You may change the order, does not matter in here because scalar transpose is scalar. That means beta 0 times z prime gamma times psi is cancelled out by this guy. So it is also simple. Minus zi transpose gamma 0 of u. Right? That much is this much. Okay? Therefore, now we are almost done. The second stage estimator is approximately minus h inverse of summation sample average of minus zi transpose gamma 0 times ui. Okay, so I will ignore minus signs, does not matter. So that means you may write this as psi I, where psi I equals h inverse of zi transpose gamma 0 times ui. Okay, but h is given here, so it equals zi transpose gamma 0 ui over expectation zi transpose gamma 0 squared. Okay, like it might be more interesting if we change this to this, right? So now then you may calculate, because we know the influence function, you can calculate the asymptotic variance, which is expectation. By the way, before doing that, let's just check. The mean is 0, which is obvious because its expectation is 0. You expectation, like x hat and u are uncorrelated, so automatically the expectation will be 0. So then the asymptotic variance is psi and psi transpose expectation. Let's do that. It is also easy. In the denominator, we have two of these guys, and in the numerator, we have expectation ui squared times xi hat squared. Okay, so it is very familiar form. Okay, as you see, remember OLS, if x is scalar, then OLS variance was exactly this guy. Okay, in other words, like in vector form, the OLS sandwich formula looked like this, right? But in the two-stage least squares case, the only difference is head. Just put head on them, right? So even if we are doing just scalar x, but even if it was vector, you will get the same form. In just the x is replaced with x head. That is the only difference. Okay. So then now let's think about it. How can we calculate that? Okay, anyhow, this is what we get. So we need to ask, just one more thing. Homoscedasticity. If you assume homoscedasticity, then expectation of ui squared given zi will be sigma squared. So expectation of ui squared given x hat will be sigma squared. So the v will become sigma squared times expectation of xi hat squared, and in the denominator there are two of them, so one is cancelled out and it will become like this. Okay. So this is also very similar to the OLS case. Okay, now how can we calculate that? So let's think about what is the problem here. Is x hat a problem? No. X hat is available, right? You may use the first stage estimator to calculate the x hat. So this is okay. Expectation is not a problem. You may use sample average. You know how to handle that. The problem is u, right? So then I will explain what you are going to do. So regress x on z to obtain, like say, just x hat, right? X hat is the fitted value from the regression. And then regress, you are going to regress y on x hat to obtain, say, beta hat. Okay? So up to here, it is obvious. Now the problem is the standard error. The main problem here is the residual in the second stage regression. The residual will be defined as yi minus beta hat n times xi hat. And this will capture approximately ui plus beta 0 psi I. Okay? The problem here is what we need is just ui, not this part, right? In our variance form, we need u. Then how can we calculate? You have to recalculate the residual. So I will define ui hat as yi minus beta hat n. And here you have to change the regressor, right? When you obtain beta, the regressor was x hat, but in the residual, you are going to include x. Beta is the same beta, you are going to use the same beta from the regression result. So this is the only difference. And then, expectation of ui squared xi hat squared will be calculated as 1 over n summation ui hat squared times xi hat squared. So simple. And of course, expectation a hat squared will be this. So it will be pretty straightforward to do this. Okay. Now, I had to erase it. I didn't erase it before. It's okay. Sorry about that. Now I will be comparing the result with GMM, right? So GMMs in general, GMMs, optimal GMMs asymptotic variance looked like this, right? And especially in the instrumental variable regression case, G was ZIXI transpose, and omega was expectation UI squared Z transpose. But we are going to assume homoscedasticity, so it will be simplified to ZI transpose. Okay, so we will consider a very general setup. Okay, now let's think about it. And on the other hand, two-stage least squares form was expectation xi hat transpose inverse expectation sigma ui squared xi hat transpose expectation xi hat transpose in general, right? And under the homoscedasticity assumption, sigma squared will go out, and it's just simply this. Okay. So by the way, they are equal. GMM and the two-stage least squares are have the same variance only when homoscedasticity assumption is assumed, because two-stage least squares use OLS, not GLS in our setup. So OLS is not optimal, not efficient when the error term is heteroscedastic. So we have to assume homoscedasticity to show the optimality of the two-stage least square. Okay. Anyhow, this is this, and we are going to start from here, right? And our goal is this will become expectation of xi zi transpose expectation zi transpose inverse expectation zi xi transpose total inverse times sigma squared. Okay, that is what we target. So from here, I'm going to show this equals to this. This idea is simple. So xi head is zi transpose gamma head. Okay, and remember gamma head gamma 0. I will write it here. It is about the limit. So in the limit, it will become gamma 0, and we know gamma 0 is OLS of x on z. So from the OLS identification, we know it is this. Okay, so it is straightforward to plug that in here. Zi transpose expectation, Zi transpose inverse expectation, Zi xi. Okay, so then now I'm going to plug this into here. Expectation xi hat transpose equals, oh excuse me, something is wrong. I'm not sure what was wrong. Let me see. The order is not right. I'm sorry, the dimension does not match. So if x is k by 1, then we had to write it as gamma times gamma transpose zi, because zi can be m by 1, so you have to match the dimension by gamma. Okay, so then here you need to write it as expectation xi transpose times expectation zi transpose inverse. Same thing, but I had to match it like k by 1, 1 by m, so m by m matrix. So this is right. Then using this form, what you get here is there is no transpose, like excuse me again, it should not be transposed. This is right. So now it's k by m, right? This is how we do. I'm sorry for the mistake. Anyhow, the dimension matches the transposition should be done carefully. Anyhow, then now the first x hat can be written as xi zi transpose expectation zi transpose times zi, right? So this is gamma times z. This much is the first x hat. And second x hat, if because you take transposition, we are inverse here. We are doing same thing in the other order, in the reverse order. That is what we do. Okay. Now, expectations are not random, so you can bring them out of the large expectation. So it equals expectation xi transpose expectation zi transpose inverse, then expectation zi transpose expectation zi transpose inverse expectation zi xi transpose. Okay, as you see, it's cancelled out. It will only have xi zi transpose expectation z prime inverse expectation zx transpose. Exactly, that's what we needed, right? So this much equals this guy. So if you take inverse and multiply sigma squared, they are equivalent.